Welcome to Chapter 11, Differential Calculus, Section 11.1, Limits.
And we're going to start out with an introduction to limits. So let's look first at the informal definition of a limit. If f of x becomes arbitrarily close to a single number, L, as x approaches c from either side, the limit of f of x as x approaches c is L. This limit is written as, what you see written below here, the limit as x approaches c of f of x equals L. So we're going to start our discussion by comparing limits and function values. If the limit of a function f of x exists, then there are three possibilities. Case 1, f of c is not defined, but the limit as x approaches c of f of x is defined. Case 2, f of c is defined, but the limit as x approaches c of f of x is not equal to f of c. And then case 3, f of c is defined, and the limit as x approaches c of f of x is equal to f of c. Otherwise, the limit of f of x as x approaches c does not exist. So when you see this abbreviation here, DNE, that means does not exist. So let's look first at case 1. Case 1 says that f of c is not defined, but the limit as x approaches c of f of x is defined. Our first limit that we're going to look at is the limit as x approaches 4. When you please see this little plus sign here, that means from the right. If you think about the x-axis, all the positive numbers are on the right. So this is the limit as x approaches 4 from the right of f of x. So we're going to travel along the curve close to x equals 4. We're just going to keep approaching 4. Now we can't see what's underneath here because we have this red bar in the way, but if we could make a guess, then that's going to be what our limit is. If we look across at the y-axis, you can see that the limit is 2. So the limit as x approaches 4 from the right of f of x equals 2. Our next limit says the limit as x approaches 4 from the left of f of x. That's what that minus is. It means left. So we travel along the curve from the left, getting arbitrarily close to 4. And again, we can't see what's underneath, but we can look across at the y-axis and see that our limit is 2. So then we're asked, what is the limit as x approaches 4 of f of x? Well, we need to look back at the informal definition of a limit. If f of x becomes arbitrarily close to a single number L as x approaches c from either side, the limit of f of x as x approaches c is L. So the limit needs to be the same number from either side of 4. And if you look at the left and the right hand limits, those are both equal to 2. Our limit then, as x approaches 4 of f of x is equal to 2. Then we're asked, what is f of 4? Well, f of 4 is our function value at x equals 4. And we can't see what that is right now because this red bar is in the way. So we're going to remove it. After removing the red bar, notice that we have a hole in the graph, or what's termed a removable discontinuity at x equals 4. So this means that f of 4 is undefined. What a removable discontinuity is a point on the graph where the graph is disconnected and you see a hole in the graph. If we wanted to redefine this function, if we knew what the equation was, we could define f of 4 to equal 2, and that would fill in the hole or connect the graph. So in this way, we could remove the discontinuity. And so that's why it's called removable, because it's possible to redefine it to where it's no longer a discontinuity. But that's not the case here. For this function, f of 4 is undefined. So we have case 1 where f of c is not defined, but the limit as x approaches c of f of x is defined. Now let's look at case 2. Case 2 said that f of c is defined, but the limit as x approaches c of f of x is not equal to f of c. Our first limit is going to be the limit as x approaches 1 from the right of f of x. So we're going to travel along the curve near x equals 1, and we're going to keep approaching. And notice we can't see what the function value is, but we can look across at the y-axis and see that our limit is 1. So the limit as x approaches 1 from the right of f of x equals 1. And then we're asked to find the limit as x approaches 1 from the left of f of x. So we're going to travel along the curve and get closer to x equals 1 from the left-hand side. And you can look across and see that the limit value is 1. And then since our left-hand and right-hand limit both equal 1, then the limit as x approaches 1 of f of x equals 1. Now we want to find the function value. What is f of 1? Well, again, we can't tell until we look underneath the bar. Notice here that we have a removable discontinuity at x equals 1, but the function is defined at x equals 1. We have this point here, 1, 2, which means that f of 1 equals 2. Now let's look at case 3. Case 3 says that f of c is defined and the limit as x approaches c of f of x is equal to f of c. So we're going to analyze this case by looking at c equals 3. So the limit as x approaches 3 from the right of f of x equals, we're going to look at the curve and we're going to travel along the curve from the right and get arbitrarily close to x equals 3. And again, we can't see what's underneath, but we can look across at the y-axis and see that our limit is 1. Then we're asked to find the limit as x approaches 3 from the left of f of x. We're going to travel along the curve from the left and see that as x approaches 3, if we look across at the y-axis, our limit is 1. So notice that the right-hand limit and the left-hand limit both equal 1. So then our limit as x approaches 3 of f of x is equal to 1. But now we want to find the function value at x equals 3. So what is f of 3? Well, we can't tell until we remove the red bar. Notice in this case that the graph is connected, and so f of 3 actually equals 1 if you look across at the y-axis. So we have the point here, 3, 1. So notice that the limit as x approaches 3 of f of x equals 1, and so does the function value f of 3 equals 1. So f of c is defined and the limit as x approaches c of f of x equals f of c. Now let's look at example 1. For example 1, we're shown the graph of f of x equals x cubed minus 1 over x minus 1. We're asked to find the limit as x approaches 1 of f of x. Well, notice that there is a removable discontinuity here. So are we able to find the limit? Yes, we learned in the other cases that the limit doesn't necessarily need to equal the value of the function. We don't have to have anything there to see that we're approaching a certain value. So what we're going to do is we're going to analyze from the right direction and from the left direction and see what our limit is. So as we travel along the curve from the right side and then look over to our y-axis, notice that the limit is 3. So the limit as x approaches 1 from the right of f of x equals 3. And then we're going to travel along the curve from the left side, and as x approaches 1, notice that our function value is 3. So the limit as x approaches 1 from the left of f of x equals 3. Since our limits are in agreement, our right and left limit, then the limit as x approaches 1 of f of x equals 3. Well, we can also analyze this limit with a table of x values and function values. And I want to show you now how to do that with the use of your graphing calculator. Calculator that I like to work with is a TI-84, and I highly recommend it for this course. So what you do is you go to y equals and you input your equation. So I hit alpha y equals to get me the fraction form. And then I'm going to put in x cubed minus 1 over x minus 1. And then let's look at the table. So notice here that the change in x is just, it's moving by 1. And so if you look at the way that the table is set up by hitting second window, our delta table is 1. So we're not going to mess with that. The way that we're actually going to change how it's moving is by down here, independent means independent variable x. And instead of it being automatic, where it automatically moves by 1, we're going to click on ask. So now when you go to your table, notice that it's blank. Another thing that we need to change is sometimes on the y column, when you do this, they'll come out in fractions. We want decimals so that we can easily analyze what our function is approaching. So our answers, we want them to be in decimals. And so now let's go ahead and go into the table. So we have 0.75 is our first x value. 0.9 is our next x value. 0.99, 0.999, 1, 1.001, 1.01, 1.1, and 1.25. So this is indeed the table that you saw pictured there. This is how you get it in the calculator. And so you can easily see that as x is approaching 1, our function is approaching 3 from both sides. One last thing to mention about this problem is that we've looked at it graphically, we've looked at it tabularly. We can also find the limit analytically, but we're going to do that in the next section. So we're going to use algebra to figure out what our limit is. Here's an example for you to try. So I'd like you to pause the video and see if you can figure out this limit and then unpause it. So after doing this on your own with the graphing utility, you should have come up with the answer that the limit as x approaches to of f of x equals 5. We'll just look at that briefly. So here's our x value of 2, if you're looking at the graph, and so we're traveling along from the right, and we get to really close to where x equals 2. We can look across at the y-axis and see that our limit is 5. And we could do the same thing from the left direction. As we approach to look over at the y-axis, and you see that the limit is 5. So that's the limit as x approaches to of f of x equals 5 using the graph. We could do it again with the tables. So as we're approaching from the left, those would be the numbers that are less than 2 on the x-axis. As we're approaching from the left, notice that your limit values are approaching. You see 4.998, that's really close to 5. If you could take a guess at what would go in there, it would be 5. And the same thing if you're approaching from the right, which would be the numbers that are greater than 2, the function values are getting closer and closer to 5 as well. 5.002 is very close to 5. So 5 is the limit of your function as x approaches 2. Now let's look at example 2. We're asked to evaluate the function f of x equals x over the square root of x plus 1 minus 1 at several x values near 0 and use the results to estimate the limit. So when we evaluate a function, that means that we plug in values. So we want some numbers that are really close to 0 on the right and left side of 0. So we could do, if we want some numbers on the right side, just for example, we could do f of 0.0001 and see what that equals. We could do f of negative 0.0001 and see what that equals. And if you use your calculator, you'll find that f of 0.0001 is equal to 2.00005, and f of negative 0.0001 is equal to 1.99995. So if you can make a guess, what number would you think is going to be the limit as x approaches 0 of f of x? Well, it's easy to see that the limit, the right and left-hand limits are 2. It's approaching 2. So instead of plugging individual numbers into the equation, which could be very time-consuming, what you could do instead is use your graphing calculator like we did in the previous examples and just set your table up to where you put x values that are arbitrarily close to 0, and then you could just analyze the function values as x moves from the right and from the left, and see that your function is approaching 2. So the limit as x approaches 0 of f of x is equal to 2, you can see from the table. We could also look at it graphically if you want to graph it in the calculator. Now on the TI-84, you don't see the hole in the graph, but if you wanted to trace, you could see that there's an error there or that it's undefined. It won't show anything for the y. But still, you can see that right here on the y-axis, this is 2. So as you're going from the right and the left, you see it's approaching 2. So the limit as x approaches 0 of f of x is equal to 2. I want you to try a similar example. Go ahead and pause your video and work this, and then unpause it and see if you get the same answer that I did. So if you did everything correctly, you should have got the limit as x approaches 0 of f of x equals 0.25. You should have gotten a table similar to this. You may have used some other numbers that are arbitrarily close to 0, but something similar. And as x approaches 0, you can see that your function values are approaching 0.25, if you could make a guess of what goes in here. I mean, these are all, the graphing calculator is already kind of doing a little rounding there because these numbers are so close to 0. And the same thing from the right direction. You can see that your function values are approaching 0.25. And then if you want to look at the graph instead, as x is approaching 0, we can't see on the graph what this is. The scale is not given on the graphing calculator, but you can use the trace feature. So if you plug in a number really close, like 0.001, that's very close to 0, notice that the y value is 0.254, it's 0.2499844, which is very close to 0.25. So the limit as x approaches 0 of f of x equals 0.25. So for example 3, we're asked to use a graphing calculator to find the limit as x approaches 3 of x minus 3 over e to the x minus 3 minus 1. So we're going to do just like we did in the previous examples. We're going to analyze the graph and we're going to analyze the table. So if you look at the graph, if you put some numbers in that are very close, 2.999 is to the left of 3, and you can see that y is equal to 0.000050001. That's a number very close to 1. So as we're moving from the left on the x, our left limit is 1. And then on the right side of 3.0001, y equals 0.99995. So again, the limit is 1, but this time we're approaching from the right. We can see that in the table as well. The numbers that are less than 3 are on the left of 3. So as we're approaching from the left, you can see on the y-axis, or the y values are approaching 1. If you could take a guess of what's in here, that would be 1. And if we move from the right of x towards 3, you can see that the y values again are approaching 1. 0.9995 is very close to 1, as is 1.0005. And we can make these x values, as close to 3 as we want to. We could do 2.999999999, and you'd get 1.00000. You'd get a bunch of zeros. The point is that you're approaching 1 for the y values. So your limit is 1. The limit as x approaches 3 of x minus 3 over e to the x minus 3 minus 1 is equal to 1. Now let's look at example 4. We want to find the limit of f of x as x approaches 2, where f of x equals 1 when x is not equal to 2, and 0 when x equals 2. Notice that there is a removable discontinuity in the graph. and the function value at x equals 2 is 0. But we learned in some of the cases that we worked on earlier that the function value doesn't have to equal the limit value. So when we're analyzing this, we're going to use the same approach that we've used before. We're going to move along the curve from the right and left, and then we're going to look over to the y-axis and see what our limit is close to that number. So as we're moving from the right, even though there's a hole here at x equals 2, we can still look across at the y-axis and see that the limit is 1. The same thing as we're moving across from the left side. When we get closer and closer to 2, you can look across at the y-axis and see that your limit is 1. So the limit as x approaches 2 of f of x is equal to 1. Now I want you to pause the video and work a similar example, and then unpause it and see if you get the same answer. So in this example, we're asked to find the limit as x approaches 4 of f of x, where f is a function whose rule is f of x equals 0 if x is an integer, and 1 if x is not an integer, and whose graph is shown below. So notice here on the graph that, at least for the integers that you can see, -2, -1, 0, 1, 2, 3, 4, 5, those are all on the x-axis because f of x is defined to be 0 when x is an integer. Otherwise, they have a value of 1, f of x equals 1. So that's why we have a graph that looks like this. And so the x value that we are concerned with is 4. We want to know the limit as x approaches 4 of f of x. Now, if you're moving from the right of 4, notice that your function is approaching 1. It may not equal 1, but it's approaching 1 from the right and from the left. If you look across, that's what's on the y-axis, 1. So the limit as x approaches 4 of f of x equals 1. And we've seen several cases already so far that even though the function value is 0, f of 4 is 0, the limit doesn't have to equal the function value. So again, the limit as x approaches 4 of f of x equals 1.
Well, that brings us to the end of this video. Please join me for the next video of section 11.1, Properties of Limits.